Yeah, good morning, everyone. We've all made it to Friday. So our next lecture here is going to be picking up with tsunamis. We'll get to in a second. Just a reminder, I've received a few emails about this. There is no, just to confirm, there's no worksheet that's due tonight. None that's due this week. Again, I gave everyone a week off after the worksheet and the exam last week. So unless anyone has any questions, I'm just going to get started with the tsunami, and maybe we can try to wrap up, on time or a little bit early today for Friday afternoon or Friday morning, actually. Sorry. So remember, we covered tsunamis. I showed you the video of the tsunami from Japan. Obviously, pretty evident how much damage is done and how much, how much of a catastrophe these situations can be. But really, the example I showed you looked at the tsunamis that are caused by earthquake events, which is displace a lot of water and cause major waves. But there's actually a variety of different ways that tsunamis can occur. Um, Key things about all these tsunamis that remain the same, just reviewed from last time, that was the fact that the tsunami waves can travel very quickly with very low amplitudes until they get close to the shore. And then they basically run into a space problem where you're trying to push a lot of water through an infinitely smaller and smaller area as you get shallow water close to the surface. And that causes the big displacement of heights and actually the drawing out of water from the coastlines. So those factors and characteristics remain the same. But really what I wanted to, and they'll be relevant to the earthquake examples. But really what I want to get onto today is talking about some of the other ways that tsunamis can occur. One of the more common ways tsunamis occur are actually related to landslides. So landslides we'll talk about more in general later in the semester. But they often happen where sediments or even solid rock become stable. There's a sort of concept called an angle of repose. It's the angle at which the material can be stable and form a slope, as opposed to when something forms a cliff and will be unstable and fall, potentially fall off. And many times, particularly in freeze thaw events, at the end of the winter, into the spring, when a lot of water is migrating, often during major storms or major precipitation events, or in fact, following earthquakes, volcanic eruptions, and things like that, you can see those landforms sort of get back to those angular repose by having a lot of material dump out. In all cases, if that debris flows into a body of water, it can potentially lead to a tsunami. And of course, just like you probably would guess, the size of the tsunami is commensurate with the amount of debris that enters the water column and the amount of displacement that's caused by that scenario. So this is an example from a debris flow tsunami from I think about 2008. You can see this is a cliff slope that became unstable, and the material flowed out into this harbor, for example. So the sudden movement of the debris into the water is what generates the wave. These can, the examples I've talked about here, I'm talking about things that are above, basically on land, above water, but these can also occur underwater. And underwater, they're called submarine landslides, but the same concepts of the angle of repose and unstable slopes are true. More commonly, the submarine landslides are triggered by events like earthquakes, but the degrees, the slope of the on the subsurface topography also can drive that as well. So one of the most famous examples is an area called Lituya Bay in Alaska, and it's sort of the site of the most famous tsunami caused by a landslide. It's also the largest tsunami ever recorded in recorded history, and occurred in 1958. So I'm going to take you through this example. Really impressive event. It actually was caused a landslide that followed on from a earthquake, a magnitude 7.7 earthquake, so a fairly big one with a lot of ground shaking. And basically, in Gilbert Inlet at the head of the bay, the earthquake was fairly local to that area. And during that event, approximately 30.5 million cubic meters of rock fell into the bay. For perspective, this would fill a National Mall to a height of about 25 meters. It would overflow the Ohio State Buckeye football stadium, right? So this is a pretty major event. You can imagine that just being dumped in a narrow inlet, and that sudden displacement caused a wave that basically was 516 meters or 1,720 feet in height. So just take a moment to think about that. That's a wave that is 170 stories high. It's an incredibly large wave. Obviously, there's not really much you can do if you're on the wrong side of that one. And as far as we know, this is the largest recorded mega tsunami ever, and clearly the largest one that's been that was recorded in recorded history. So, for perspective, this wave at 1,720 feet tall had enough power to snap off trees and completely break, almost everything off up to that height. Amazingly, there were some fishermen who were actually actively out on boats, were out at water and weren't subject to the big waves. They basically got sloshed around as the wave came back, and many of them actually survived and were able to basically tell the story. So to give you a perspective here, this is the Lituya Bay, this is Gilbert Inlet, and this is Gilbert Inlet, and the rock slide occurred back to here, leading to waves, tsunami waves, that made it all the way out to the area. So out of the sort of Gulf of Alaska, you see the waves are only about up to 30 meters high. But back here is where the devastation was, really, really profound. I get some videos of this, but this is an aerial image that took place after this. The scale is pretty bad on this, but this is a few 1,000 feet of the mountain slope where the trees and material were wiped out as a result of this tsunami event. So just similar to the earthquakes, I'm going to give you a video here of a underwater tsunami. This one, the slope failure is what we call this. You notice this is recreating that angle of repose here. And in all situations, that displacement, same exact scenario, can cause the water column to locally change and catalyze a tsunami. In terms of landslides, we actually think today these are amongst the greatest potential for tsunamis that there are. If you've followed any of this in the popular press, the Discovery Channel did a big series on this in the La Palma, Canary Island volcanoes just off the coast of northwestern Africa. And they propose that, similar events like this on volcanic slopes that are sort of unstable and have activity might actually lead to sort of mega tsunamis that could reach as far as North America. So that's a good segue, I think, into thinking about the next vector of tsunami formation, which is tied to actual volcanic eruptions. So in many of the same factors are true in the volcanic eruption scenario for tsunami. One of the biggest hazards that are tied to volcanic-induced tsunami events are the fact that the slopes often get a lot more material on top of them during eruption, and they can become unstable. There's also direct explosion and/or what we call caldera, or the what we think of as the volcano failure. We'll talk about volcanoes next week, but this will give you an example of how volcanic eruption can cause a tsunami event. So since it's erupting, right away you have unstable material that can flow and cause a tsunami event. Right, so that can lead to a major catastrophic tsunami, in fact, but also in many cases this slope will fail. If you remember, and you'll see examples of this next week, but if you remember seeing imagery of Mount St. Helens failing, the slope actually blows out the side, and that could lead to some really large eruptions. I think a lot of the mega tsunami concerns of La Palma Islands and how they could affect North America might be a little bit overblown on a human time scale, but the reality is, people are monitoring it very carefully because there's both a critically stressed slope geared to fail around the idea of regular landslide, but there actually is evidence that this one side of the caldera is shifting down, so people are expecting that could be a sort of a double punch, if you will. So just like other aspects of earthquakes, there's regions that are far more at risk. Obviously, I think it goes without saying, if you're not near the coast, historically, you have very limited concerns of tsunami. That example in Lituya Bay, of course, it's a very steep slope there, and actually there wasn't much damage away from the coastline. But there is concerns, in particular, like I mentioned, this area of La Palma here, even though they're considered to be low hazards. Other folks have different opinions on that, and the projections if that failed could lead to flood, tsunamis that are expected to be even larger than Lituya Bay, and have potential risk to do more damage that's further inland. But I think that's fairly low probability as indicated in the risk map that's presented here. The other aspects of that, of course, though, are areas that are very much at risk. Where geology is active, It's big, it's strong, and it does a lot of, it has the potential to do a lot of damage. So the Pacific Ring of Fire here, or Rim of Fire, whichever you want to call it, around the Pacific Plate, where you're seeing subduction on both sides of the Pacific Plate. That's an area, just like the seismic hazards we talked about earlier, has great potential for tsunami events. In fact, most of the tsunami is a Japanese derivative. It was derived from Japanese language. It's Japanese word, and as a result, it's not exactly a small coincidence that it's within an area that's at most risk for those areas. Hawaii, for example, in the middle of the Pacific, actually has some of the most frequent number of tsunamis because even though they're not all very big, basically anywhere in the Pacific, they're within it and can kind of see the displacement of wave water towards the tsunamis. So, obviously, coast and proximity to major subduction zones are the most at risk. Divergent plate boundaries, such as the Atlantic, tend to not have nearly as much tsunami risks. But in addition to subduction zones, the other major risk factors are landslides and volcanic eruptions. Key thing there is that the earthquakes and the volcanic eruptions are also, predominantly along the Pacific Ring of Fire. So not surprising that there's a higher likelihood of those events occurring near those areas. So, within that context, of course, any region that's close to an active plate boundary is at risk. And one of the most unfortunate and dramatic examples of this problem, certainly during your lifetimes, although you might have been a little bit early to remember it actually happening, was actually occurred in the Indian Ocean, which we'll talk about here in a few minutes. So, any place that there's near a plate boundary, there is certainly risk. So without any more segue into this, one of the most famous tsunamis now recorded, and certainly one of the most devastating, was the 2004, Boxing Day, which is a British word for the day after Christmas. So December 26, 2004, and there's a tsunami, basically the intersection between the Indian Australian and the Indian Australian plates here, and basically is right in this area of this transition. There's some microplates that are broken up in that area, including the Burma plate. And effectively, right here, as you see in the star, that area is where the earthquake occurred. In basically, in an instant, the Burma microplate moved 20 meters up and to the west and southwest. So that's 20 meters is 60 feet. It's not miles, but it's a really big displacement of rock. Imagine if your house moved 20 meters, that would be a pretty devastating event. It actually was the largest earthquake recorded on Earth in the past 4 decades. I think since 1963. It was a 9.1 magnitude earthquake, which actually, for perspective, the scale of this, it was large enough to actually see some wobble of the poles at the time of that earthquake. That was the degree of the strength, and had numerous aftershocks of degrading magnitude down to about 4 for about half of a day. So again, the key activity is the India-Austral plate interacting with these series of microplates. It has been a very active area long term. There's a lot of seismic activity in the area, but this is the first tsunami of this event that was really observed. It was the most devastating also, which we'll talk about those aspects here in a second. 250,000 people lost their lives instantly, and I think this is my my sort of pet peeve, is that we do a really good job of recording how many people died at the event. But what we're going to talk about a lot in today's class is thinking about the sort of environmental ecosystem damage and how many people are sort of derivative lives lost as a result of issues related to that. So it's the same things we talked about in last class. Poor water quality, infectious disease, waterborne diseases, and unfortunately, because people have now been uprooted, there's major devastation. There's often a component of violence that follows these not violence in a military sense, but violence in the sense of people who trying to steal materials or basically scavenge for out of necessity, but as a result leads to a lot of conflict between people in these times. So in the perspective of what actually happened, this 20-meter displacement both up and to the west actually occurred about 30 kilometers below sea level. That's a pretty good distance. The ocean's not quite that deep there. That's obviously in the subsurface of the Earth's oceanic plates. And basically, that 20-meter displacement's huge, but it also occurred along approximately 1,000-kilometer surface, slipped all in one direct motion, which caused pretty incredible amount of waves. Basically, what you could see here is that this basically relocated about 30 cubic kilometers of water to trigger the tsunami, and actually, for the record, permanently raised the seafloor in that area. So that the rock's actually been displaced such that in that area you can still see nearly 20 meters of displacement. And because of the repositioning of the ocean bottom, it permanently changed the global sea level by about 0.1 millimeters. That might not sound like very much, and it really isn't on a global scale, but it's pretty impressive to think about an event in one area that actually causes the whole global sea level to be reconfigured, if you will. So, to put this in perspective, how violent are these? How much energy is dissipated? If you could have captured the energy that occurred during that tsunami event, it was equivalent of 370 years of all the total energy used in the United States in the 2005 levels, which would be like 350 years of modern use, something like that. So for perspective, we're talking about a major energy event. Obviously, there's not a way to capture that energy, but it surely is something to be, gives it a perspective about just how much damage really happened there. So, in perspective, this these lead to massive tsunami waves that, of course, are sort of nominally concentrical initially near the zone. The damage onto Indonesia was obviously profound, but the nice thing for folks in Malaysia and other locations, of course, is that is actually the waveforms are basically stopped by the landforms, and as a result, there was the folks further to the east weren't affected by this. But this wave traveled. These are sort of isopac lines. It basically means a line of equal height or equal time or equal something around that area, and basically you can see here within a minutes this was onto the shores to the east. And here at an hour it was already in Myanmar, Thailand, and within a few hours into Bangladesh, India, Sri Lanka. And if you notice here, actually most of the, or not most, but a large number, in fact, most of the deaths were in Indonesia near the event. But outside of that, even though there's a 2-hour warning time, most of the longer term deaths were tied to people in Sri Lanka who really weren't even prepared, didn't really even have any notice it was coming, even in a few hours. So this event, for perspective, took 7 hours, but actually reached the shores of Somalia and killed individuals, along these areas. Even with that amount of warning time, there's still not a lot to be done to prevent this scenario from causing a lot of damage. So, for perspective, the wave that hit Indonesia, not surprising, you have 167,000 deaths there almost instantaneously. But when you look at it compared to that, these are still incredibly large waves. 10 meters is, nominally 30 some feet in India. But, for perspective, notice that the waves out in Sri Lanka are, in the less than 5 meter range. And actually that's where a lot of the death and destruction occurred. In terms of economic costs, it was obviously in the billions and billions of dollars. I think it was $8.7 billion of damage from the one, singular event. So give you some perspective on just how much damage occurs in these situations. It's not just the initial wave damage and the loss of infrastructure, roads, vehicles, and things like that we saw last time, but it's also sort of catastrophically changes the coastlines in many cases. So this is an area of Indonesia called the Banda Aceh, and the Banda Aceh, this image on the top is actually what it looks like on Christmas Day, and aerial imagery. There's an active area, pretty a lot of activity. And then by the end of the next day, a couple things I want to draw your attention to. One is look how much smaller this island is. A lot of the material is literally wiped out. It wasn't just the wave crashing over the top of it; it literally eroded all the homes, all the infrastructure, and most of the actual land surface. You can see here these trails of dust where it's continuing after it gets broken up to wash out to sea, and also where it's been eroded under the area. So, you know, the initial wave does a lot of damage. There's also a occurrence of subsidence where this material gets washed away, refills with water, and the whole area starts to sink a bit. Excuse me. Sorry, I'm having a little trouble there. But the key thing I want to point out here is that even though this is, even this is incredibly changed, it's actually still, there still is an area there that, you can see the islands out in the margins that where this area used to actually be present. So, some of the things to consider is what are the actual economic and environmental impacts of a tsunami? And for an economic impact, there can be exceedingly high at local levels. Typically, they do tend to be, in fairness, relatively minor at the national level. Industries like tourism, fishing are often the most, or actually also trade. So port cities and stuff like that can be most affected. But in reality, in most countries, they represent a relatively small fraction of the global domestic product, or even the national domestic products. So, in essence, an economic impact can be extreme in localized areas, but often is relatively minimal on the broader scale. Obviously, from environmental impacts, it's hard to go beyond saying most of the island is wiped away, right? It's fairly clear how much that impacts the environment. But some of the other factors, other than major catastrophic erosion, problems to infrastructure, homes, and loss of human life, is that there are some greater effects here. I talked about this in the video last week, but when this ocean water, which is high in salinity, we all know it's salt water, right, flows over the land, it actually sort of salts the earth, which is, if you remember that phrase, it's not a good thing. And what ends up happening is that not only do you remove a lot of the soil and vegetation that can lead to enough organic matter to create a viable, vegetation, it also puts salt water into the soil and into the water. And that causes sort of a multi-decadal problem where until enough fresh water comes in and flushes that out, that salt water will perpetually preclude vegetation, and the water is no longer potable, and it needs to be filtered and treated to remove salinity in order to actually drink it again. So, obviously removing the land is a big one. One of the ways this leads to other health crises, of course, is that you are, you're actually ruining the drinking water supply. So imagine you've just seen, 2/3 of your island get wiped out, and for weeks you will not be able to find water that's not too salty without aid. So it creates a lot of very rapid migration of local populations in those scenarios. Some other things that are affected. You have ecosystems that are wiped out. A lot of the mangroves, coral reefs can be entirely obliterated during these events. The forests can obviously, a lot of trees get knocked down, particularly with close to the coastline. Sand dunes, coastal wetlands are often damaged, and of course, in the sort of what we call brackish waters, they're waters that are at the interface to fresh and salt water. They're fairly niche ecosystems, and often those become too salty and can be sort of permanently damaged or damaged for succeeding in long times before those ecosystems recover. The other factor here is that we saw this in the video. You can see everything from knocking down infrastructure, buildings, homes, etc. You can often see fires start to form because of the pipelines and electrical wires being damaged. The other aspect of this is that and we don't think about this very much probably day to day, is that there's an entire ecosystem where we're thinking about there's entire watersheds that have water moving around, which we'll talk about these things more in the semester. But there's also sort of you can think of them as a sewer system, if you will, right? I mean, they really are sewer systems. But think of them as the whole integrated waste management systems. If you're in an area where there's actually integrated systems for gray water removal, like storm water, for river drainage, so the drains you see along the road, and actually fecal and other solid waste matter, these can often be affected. So imagine these things are designed to basically let things flow downhill, typically out to oceans or to treatment facilities, and then on to waterways or oceans. When you have major water events where these things get flooded, you actually can kind of stop or even reverse that process, which, in addition to the salinity that goes into the soils and aquifers, or, groundwater, you can often put in relatively large amounts of solid and liquid waste. In many cases, high concentrations of industrial chemicals, can be spread around everywhere. The other factor here is that this often mobilizes a lot of sort of fertilizers and nutrient pollution from farm fields, because it gets washed out and gets displaced everywhere. The point I guess I'd like to make here is that, we tend to think of these things as happening every once in a while, but the reality is the damage is sort of multi-decadal. You're seeing a redevelopment of Banda Acai today, which I'll show you a photo here in a second, but it's changed it in a lot of ways. Longer term, after we get past this initial crisis, from this perspective, it's not just the roads and the cars, which we can do relatively easily on a few year time scale. It's also the big capital infrastructure. We call these capex infrastructure, but sewage treatment plants, power plants, water treatment facilities, all those become major concerns and often lead to incredibly long environmental and economic impacts. So, the top picture here gives you an example of from Banda Acai, just how bad things were. This was sort of in the center of that island. Some buildings survived reasonably well, but you can see that sort of the indiscriminate damage. If you want to look at comparison, this is actually 2019. I grabbed this image, but it's now a return to being a tourism destination. It's obviously been significantly changed, but and it's been successful now. But there are a lot of things we're not going to have to consider now. They have to filter their water. Now they have have lost their natural vegetation. It's not that we can't sort of be reborn, but we have a lot of work to get there. So, broadly, talking about the issues related to the immediate damage and how that recovers, this gives you an imagery of from Sumatra and just in the Acai province in this area. You can see the vegetation came right up to the coastline. A lot of this is actually coffee trees. The initial tsunami itself actually wiped this out for a pretty extensive period of extensive distance away from the coastline. So, for perspective, this is 2 kilometers. You're talking probably about 2 to 4 kilometers of damage away from the coastline. That's fairly immediately after that. So that's December 13th. Here's the end of the month of December. And notice that by 10 years later, you can, if you take a step back, you can still see the vegetation is not quite returned beyond that boundary. You see the much more plush green areas back that weren't affected, and you see this sort of lighter green area. There's a lot of factors for that. Some of them include, excuse me, I'm having a lot of trouble with this key today. Some of those include the fact that you actually have, wiped out the soil, you wiped out the vegetation. Those are obviously the big ones. But the longer term effect that's actually happening in this area is that the salinization of the soil and groundwater remains an issue that's preventing the vegetation from taking off. I mean, relatively speaking, in the absence of the salinization, these vegetation can be reformed a lot faster than can when salt water is involved. Other things I point out. Look at the levels of erosion that occur here, right? I mean, before this, you're seeing one pretty muddy river coming out in this area. Most of the coastline looks pretty much like blue water. Shortly after this, you lost this vegetation. You're seeing this erosion all along here. Notice, I mean, that's obviously a single shot, but it's pretty emblematic of the problems that occurred shortly after this. So what do we do about this? We talked about making folks aware of hazards in terms of seismic hazards, the likelihood that we can predict them, the ways we're going to predict if there's going to be an earthquake. And I told you, I think that the reality is that those efforts are fairly bleak and quite frankly, um, don't have a lot of great potential for predicting when earthquakes will occur. Tsunami warning systems, despite the fact I just showed you an incredible amount of devastation in Sri Lanka hours later, and loss of life, and on the east coast of Africa, 8 hours later, these have been fairly well developed. Obviously, there's still all the sort of issues that face social justice and equity, where they're very well monitored in places like Hawaii or Japan or the west coast of North America, and significantly less well monitored in areas like Sri Lanka and East Africa. But there are some pretty sophisticated warning systems. In reality, we still can't predict the earthquakes or the landslides, and in many cases we can't predict the volcanic eruptions. But once a major change once a major displacement of water tied to the tsunami is generated, we actually have a fairly sophisticated approach for monitoring for tsunamis and sending out local and global excuse me, local and global notices and warnings of the tsunamis. So, in the places like North America, Japan, that's great. The message get out there. We have TVs, radios, etc. It doesn't necessarily do much for folks that are, don't have radios or televisions. So, but the way this works, there's really a few different devices. Some of them are actually what are called flotation devices. What they are done is they're basically mounted on the bottom of the seafloor. They have a battery to charge them, computers to monitor them, and they send signals by satellite or by cable back to other sensor systems. And then there'll be an extension of a cable, and that'll take you up to a flotation device. And basically, what happens is that sort of monitors the pressure and the extent of that cable, and it can detect very minute changes in water pressure caused by passing tsunami waves. So these can be, for example, as small as 1 centimeter variations in the tsunami waves, which is actually relatively easy to do out in the deep stagnant ocean where the waves aren't moving around as much. And basically, there's entire networks of these things, particularly around the area of the Pacific, where there's the greatest risk. And then basically send signals back to say, okay, we're seeing this change in this area. It's probably not enough for one of the pressure recorders to observe this, but in many cases, given there's enough of these in the network, they can predict where a tsunami occurred. They can also look at the relative displacement. So if they can, although they can only displace or determine a displacement of about 1 centimeter, they can actually, give you an indication of the magnitude of the tsunami at the time. These are often paired with what we call communications buoys. So these communication buoys can either be done by radio signals to the antennas or by direct cable. But usually what these are they're anchored, and they actually sit out floating in the ocean. And not only can they receive data from the ocean floor, but they also can, now they're a little bit more sophisticated, they can actually have a global positioning application where they can determine how much displacement is occurring at the surface to similarly project how much the likelihood that tsunami events come through, or that a wave form that appears like tsunami is coming through. In all cases, these networks are of course dependent upon where they're located and how well they're operated. All right, so this is the Pacific network. You can see right here in Hawaii, it's very well. I'm not saying it's going to be any better protected from the damage, but it's clearly a scenario where there's a lot of instrumentation around it, both tidal sensors, deep ocean tsunameters, and seismic stations. But this is the network you'll notice here along the coast of the United States. We have a great number of these tidal stations looking at tsunami waves, giving us at least some opportunity to notify people ahead of time this is occurring. There's an intense seismic networking, global networking of seismographs that are geared towards looking for tsunamis. And the reality is, if you project from assuming a volcanic eruption in Hawaii, for example, was going to kick off a tsunami, you can the estimated travel time is shown here. And this kind of gives you the sense that we have about 5 to 6 hours of using Hawaii as a position for a predictable tsunami. about 5 to 6 hours before it hits our coast, and relatively well instrumented for predicting those hazards. Some of the areas can, of course, be much longer than that, but the point is, it's a growing network. It improves all the time, and there is, potential to at least warn people before the wave hits. One of the things I mentioned this earlier, but I wanted to re-highlight here is that, notice, in some sense, the global population is quite lucky that this happened over, near Indonesia. Not to imply that the Indonesians didn't suffer disproportionately, but that event was actually, about 2/3 of the area was very quickly muted by Indonesia. If this similar event happened in Hawaii, it could have been a profound level of devastation, because it would have been able to expand across all the Pacific Ocean, in all directions. So, that's one of the reasons. It's not just because Hawaii has a lot of money or a lot of pull to get, federal resources to instrument it. It's also because of the fact that an area like that could lead to, sort of incredible level of devastation. So, the monitoring systems now are starting to advance. This is really the last 10 to 15 years. There's sort of a couple other additions that have been part of this. In addition to the buoys and things I mentioned earlier, there also are sort of buoys that have global position systems, so they're actually continuously monitored by satellites and can measure smaller and smaller every year, smaller and smaller perturbations. And this has improved our capacity to notify people. I'm going to go back to this map here for a second. This is sort of the example of what could happen. But, other than the fact that there can be landforms that will break the wave down, there's also the advantage in a lot of the oceans that there's turbulence, right? That there's actually some interference for these waves that on occasion can cause the wave patterns to be broken down. So, other factors that are relevant, although to much less scale than the occurrence of high magnitude earthquakes or volcanic, or landslides, is the fact that, if you're in a scenario where there's not a lot of precipitation or storm clouds or high waves in the Pacific at the time, that can lead to greater transmission of the waves. If an earthquake would happen during a storm season, there's more wave activity, that can also interfere with the tsunami waves and break them down further out in the ocean. So it's sort of that's not really going to help us predict hazard. It's not going to help us prepare to deal with it, but there are some factors that can minimize this. Basically, the more energy that's in the water, already existing high wave areas, for example, they can sort of mute the effects of the tsunami. That's going to be the last of the lectures for today. We're back on schedule for the semester now. Next on Monday, I will be posting. On Sunday, I'll be posting the new worksheet and the lectures for volcanic hazards. And on Monday, we'll start talking about volcanic hazards for most of the week. So it looks like we did manage to finish a little bit early today. I hope everyone has a great weekend and enjoyed the break from the worksheets for a little while. I'll talk to you on Monday. Have a good weekend.